Okay, we're going to get started. Welcome to our webinar, hosted by the University of Washington and the Norwegian Roads Administration and WashDOT. We are very excited to bring to you the Enabling AI and Machine Learning to Address Transportation Challenges webinar, International Perspectives from Washington State and Norway. Oh, sorry about that. A little bit about PacTrans, who's hosting the webinar today. We work at the University of Washington. We're part of a university consortium of universities in Washington, Oregon, Idaho, and Alaska working together to research and to develop new workforce development offerings. This is an overview of our agenda today for the webinar. We will have 4 presentations. There'll be 5 minutes for questions at the end of each presentation, and then there will also be opportunities for presentations or questions at the end. Our speakers today are Christian Shetna from the Norwegian Public Roads Administration, Garima Tawari from WashDOT, the Washington Department of Transportation, Yin-Hai Wang, a professor at the University of Washington, and Germond Jacobsen, a Norwegian Public Roads Administration staff. The way we're going to approach questions today is if you can put them into the chat, and then moderators will ask them at the end of each person's presentation or at the end of the webinar. And please keep your mic on mute unless you're asked to speak to the group. Okay, we're going to welcome our first presenter, Yin-Hai Wang, to talk about edge computing and AI applications for transportation.
Thank you, Melissa. Could you please allow me to share my screen? Okay.
Yes, you're able to share your screen now.
Okay. So you see my screen now?
Yes.
All right. Hello, everybody. Welcome to the PacTrans and the Norwegian Public Road Administration and Washington State DOT joint webinar. So we have been doing this, last year. So this is our second webinar together. So today we focus on how we could use AI to address transportation challenges. So I would talk about how agentic edge AI could be used, as the cornerstone for the next generation transportation intelligence and the digital infrastructure. So we're facing a lot of challenges, particularly the aging infrastructure, the workforce challenges, the natural disasters, and limited resource. How could we use limited resource to address all these critical challenges? That's an important task, and we could leverage the AI technologies to help us find the best solutions. Maybe you still remember last this winter, in the West Washington area, we had a big flooding. So this is actually a picture. And this flooding itself cost like over $182 million damage in infrastructure. So such things is really becoming frequent. So that's just an example, right? So maybe you still remember the I-35 West bridge collapse in 2007, and people estimated the delay loss because of the collapse of the bridge on the economy is $1 million a day. So you can imagine how much loss this particular infrastructure failure has cost. And similarly, recently in 2025, this Huntsville Bridge collapsed. And this was just several months before the scheduled maintenance. we can imagine if we could recognize the risk and do the maintenance several months early, we could avoid this tragedy. In our transportation work zone area, so we also see a lot of people lost their life, right? So this is actually the numbers just in 2024. But these things, I would say, we have ways to overcome the problem, and we could avoid the tragedy from happening. So now let me show you a video. This is a big crash in 2022 in Pennsylvania. So I will not be able to play the complete video, but this video will take about 3 minutes. And certainly when this video was recorded, it was not the beginning of this crash. It was not the end either, right? So you can imagine this lasted for, multiple minutes at least. Um, you know, and it cost like 6 people's life and over 50 cars crashed altogether. And then we would ask ourselves, right? So we're facing a lot of challenges, from the flood damage to the infrastructure, to the collapse of the bridge, to this kind of, traffic crashes, and the number of people killed in work zone. So these things could be avoided, right? If we have the right technologies in place. So could we do something to prevent this from happening? So I've been thinking about this, and my research lab also work on this, try to find a solution. So logically, we want to see what's going on the road, right? So like, what's going on the weather side, the environmental side. So we need to do the detection. After we collect the data, we'll do the analysis, right? So we see what's going on. And then we need to make a decision. After you have a decision, for example, the big crash, on the I-82 in Pennsylvania, if we decide to maybe close the roadway or lower the speed limit, we need to communicate with the corresponding, control devices and take some action. And we need to observe the action and then go back to the cycle again, right? So what is the best technology for this? No matter what you use, you have to consider you need to have like data, right? So this is how the traffic sensor coverage look like in the whole country in the United States. Even though looking at this particular map, you feel, oh, we have a lot of places covered. But if you zoom in, you will feel very differently, right? So let's say we zoom in into the Washington State's case. This is actually how sporadic we have for the sensor coverage. And the coverage is pretty much in the urban area. In the big rural area, actually, we don't see a lot of traffic sensors there. So why rural areas are lack of traffic sensors? So we know normally sensors need to be powered, right? So there may be no power in the area, or there lack of the broadband communication system. You need to transfer the data or transfer the video back and forth, but you don't have the communication infrastructure. Or the installation cost is very high, right? So if you see I have to link the power to the installation side, or I need to maintain the sensor, you have to travel from a long distance. That will increase the installation and the maintenance cost. And certainly rural area is very big, right? So very low population density is a big area to cover. And the environmental factors also come to play, right? Cold winter, windy days, etc. And people also saying their lack of operation, control devices, we need data to support, and therefore the return is low. So maybe we don't need to invest that. is that the case, right? So even though this is actually what I summarized from different reports and put together the reasons on this, you look at this is actually the traffic crashes, based on the fatalities per 100 million mile vehicle travel. That's the data from 2016 to 2020. You can actually see the rural community, their fatality rate is much higher than the urban fatality, right? So based on this chart. And then we should really do something in both urban and rural area, and particularly in the rural area. So this is a map showing like the high bandwidth, like a communication network. So this is actually a pretty good coverage. Most of the places have something like a 3G, 4G, or 5G communication network. That means if we do not rely on fiber, we only rely on cell phone data, we could do something, in this area, particularly the rural areas. And then we've been working on some technology, right? We consider the connected vehicle technology may be helpful, but how could we make this simple and affordable, right? So we would imagine some magic device, and this device could be communicating with the vehicles on the road and also active users with their electronic devices. And we consider this could be something, like we call it a smart hub, and we could communicate with the traffic management center if needed. But in most of the rural roads, you don't have this kind of coverage or like a particular center to manage these places. So we feel this particular technology need to have the functions like perception, also understanding what's going on, the comprehension, need to be able to infer what's going on, even make a decision without, like traffic engineers help, right? So interacting with the road user and be responsive quickly, right? So this technology, we feel the best will be the agentic edge AI. And this is actually something we feel have a lot of future. So let me show you quickly, because given the time constraint, I just want to show you quickly how this technology could be used. We have been doing this over the past 10 years and see this has been very successful in a lot of applications. So essentially, this particular technology, you need an edge computing device, right? This could be the NVIDIA Orion, and you could do the solar power driven. Actually, we have quite a lot of places using solar power, and it's been working well. And you have the functions like computer vision, combined environmental sensing, edge computing, AI, and you do the sensor fusion on the same device, right? So you could build such a system, make it a kind of computing platform, flexible to be collecting different kinds of data, communicating with the traffic control center, or communicating with the roadway user. So we could gather data and also do the data analysis, making decisions all on the same device. And this device could have all these things done without even communicating back and forth to the cloud or to the traffic management center. And this is actually an example of the solar power, installation. And you see actually the installation cost is lower than, if you use the regular power. And I will quickly run through some of the application scenarios. You see, like this is for traffic detection and counting, right? So even with the strong pavement reflection, the result is also promising. And sensing the roadway surface condition, sensing the environmental condition. For example, you could detect how far driver can see, right? So this is actually a research product implemented on the Edge AI system. And we also get a patent recently for this technology. And the accuracy is not perfect, but it's sufficient for us to use for traffic operations. And detecting intersection, vehicle movements, try to predict near misses. And you could do something on the traffic control side to prevent a vehicle from being trapped into the dilemma zone, or like prevent vehicles from colliding into each other. And deploying the sensor, along the curb side, you could detect, how many vehicles occupying the curve, how long they take. So this has been actually a pilot application in the Midtown Manhattan in New York City. And this has also been very successful. Another very interesting application has been, like working with the Washington State DOT, try to capture people vandalizing the traffic sign. So this is an example, right? So the sensors being deployed in multiple locations and actually generating the alarms to the state patrol. If they identify some people vandalizing the traffic signs, and people would know, and they could go to stop them. In addition to like all these applications, implemented on the device, that's like you have your cell phone, like your Apple phone, you have a lot of different apps, right? You can choose which app to run. So this will make the sensor more useful because you could be detecting different objects and collecting different kinds of data. And you could also use the app, right? So this is the application, we implemented. Like this is actually the Lakemont Boulevard in Bellevue, the sensor locations, what kind of events are detected. So the sensor is being piloted, deployed in Yakama Nation, a federated tribe, and get very good data, right? So for this intersection, there were 8 people killed in 20 years. So after we have the sensor there, we have a lot better understanding about what's going on, and we can collect the data and make the right decisions on how we could improve traffic safety. And this effort, we received the Federal Highways Innovative Project Award, and recently with the collaboration with the Washington State DOT and the technologies startup company called AI Vision. So we received this Washington State Safe System Champion Award last year. I just want to share a bit more about this, the technical challenges of this technology. Given the time constraint, we're not able to go into the details. But in general, we need to deal with the resource limits, right? So because we're computing on a small device, this could be Raspberry Pi, which will only cost you about $50, or like powerful NVIDIA devices, right? So, but no matter what, they're not comparable to the server or cloud computing power. So we have to deal with the resource limit. We also need to deal with the device heterogeneity because different devices will have different settings. For your solution to be universal, you have to deal with them. And there's also scenario variations like deploying in different places. You may have to adjust the app to make it work well. So I also want to emphasize the importance of the domain knowledge, right? So this is the left side video is actually the direct implementation of the YOLO model. That's off-the-shelf computer science technology. And the right side is actually, our model. You see the left side, we miss a lot of pedestrians, right, on the road. But on the right side, we get basically everybody detected. Now let's come back to this original, like the big accident we talked earlier, right? So in this particular case, if we use this edge-based technology, we'll be able to detect when the snow starts, right? The visibility goes down. We could generate a visibility warning, right? When the snow fall on the ground, you see the roadway surface become very hazardous. You could generate a road surface condition warning. When the first crash happened, you could generate a road crash warning, right? So there are multiple ways for us to do something and with enough at the time, try to prevent this big tragedy from happening again. So, so interestingly, I posted this and we got a response, say somebody like say transitioning to AI-enabled infrastructure is the only way to move from reactive to proactive safety at scale. So I agree with this guy, and I do feel this technology has a lot of potential, to be important, unit stone or cornerstone on our infrastructure network, try to help us implement, our digital infrastructure system, smart infrastructure system, or even help, to address like a lot of new demand with the new transportation needs. So the market is huge for this. And most of them could be done, using this kind of edge technology. And finally, I just have 4 different summaries for you to consider. First of all, edge AI has been proven to be, flexible and effective. And it has a huge potential in roadway safety and mobility enhancement. And this agentic edge AI empowered system are the future key elements of the smart infrastructure system. As you can see, it can detect, understanding, and make decisions, right, without human intervention. And transportation domain knowledge is important. This is not something we can just leave to other people to do. We have to use our domain knowledge to really make the system to be working well. And the research spending in this particular area, I think, will grow. I just came back from ITS America's annual meeting yesterday, and there's just a lot of emphasis on digital infrastructure, how we could make the work zone smarter. So I will stop here. Thank you very much, everybody. And interestingly, we work with WashDOT, we work with Norwegian Public Road Administration. The research I presented got sponsorship from both organizations. Thank you very much. Any immediate questions? If not, Melissa, let's move to the next one so we have more time to do the panel discussion.
Okay, we do have one question,
Okay.
which is in case of detection, we know that there is a trade-off between accuracy and inference speed. How edge and agentic AI deals with this fact?
Actually, I would say agentic edge AI is very flexible. To improve the detection accuracy, you need to be doing some transfer learning and collecting some local data to learn. In terms of speed, it's almost always beat the cloud-based solution because everything is computed locally and the edge device could be responding to the road users' needs very quickly.
All right, thank you. And if you could stop sharing your slides,
Yeah.
we'll have our next presenter up, German Jacobsen. He'll be talking about Norway's Public Road Administration's AI policies.
Thank you, Melissa. Can you see my screen?
Yes.
Yes, perfect. Thank you very much for having us, and good morning and good afternoon to everyone. So I will talk a little bit on how we at the Norwegian Public Road Administration have been working especially on computer vision for the last couple of years, and very in line with what the previous presenter Inhai was talking about, and how we can improve and the infrastructure in Norway. So as probably a bit background on the Norwegian Public Road Administration, we have a responsibility in improve the transport system in Norway, and we need to make sure that we have predictable and efficient and safe travel for people and businesses. And of course, Vision Zero is one of our most important areas. As previously shown, there's a lot of accidents and injuries, and we need to find out how we can prevent these accidents. And then the climate and environment. There is a lot of challenges when it comes to the nature, and we have to ensure that we don't have any loss of biodiversity. And to help us do that, in Norway we have a national transport plan, and in one of the policy goals is to use of new technologies. And this is a help for us to be able to shift the way that we work from a more traditional way of current manual processes to push ourselves to use new technologies, even though they might not be the easiest to start with. And we all have felt the pilot disease, pilotis, and this is one of the ways for us to then push in the right direction. Norway is a long country, not that big, but it's very long, and we do have a lot of roads. Norwegian Public Road Administration, we have a responsibility beyond the roads that we own. So we are an infrastructure developer and operator for some roads, but also we have a national responsibility when it comes to the regulation and responsible for approvals, inspections, and so on. And of course, also we have a responsibility on a national level when it comes to advisory and competence, or as a competence organization, developing standards and best practices and efforts for road traffic and transport. And we have 10,000 kilometers of our national roads that we in the NPRA maintain. But then we have 40,000 kilometers of county roads. And then we have a 50,000 of municipality roads. And then with the top of the private roads, that's 100,000. There's a lot of roads that we need to maintain. And one of the things that also was High was showing that there is the areas where we actually have cameras and equipment where you can actually see what's happening is very few compared to the number of kilometers of road that we need to maintain and have an overview over. So how do we then do the job, not just for NPRA, but for the transport and road system in Norway? And of course, AI is not new to NPRA. We have a good starting point. We've been working a lot with experts as the University of Washington and many others for many years, and the Norwegian universities and entities and other private companies. And we've been testing a lot, and we've been doing things for many areas. But we're now in a process of building more capabilities to be able to actually consume and put these pilots and solutions that are more separate into a more unified system. So we need to go further. So we need to focus now on the real world applications and what's important for NPRA. And that means that we need to scale the good solutions and really get the good benefits. And of course, leverage even the more of the opportunities. So why is it important for us? We have a lot of snow, we have a lot of roads, we have a lot of equipment along the roads that we need to maintain. And this is my version of the digital twin. So we have how it looks today. It's not the weather in Trondheim is much nicer than on the picture today, but we always have to know what kind of road do we have? How many lanes? How is it divided? Is it speed limits? What kind of rules do we have? What are the conditions on the road? Who is driving on the road? Is it slow and fast, and so on? And accidents. And we also need to know the condition of the road. We need to find all the different areas where we need to improve the road infrastructure. And this is what I would say that's part of the digital twin that we need to constantly try to capture, constantly try to reach that level of a digital twin that is as equal to the reality as possible, to be able to then actually do the job and to simulate and to process and to make good decisions. And how do we do this? We have, of course, a lot of collection solutions. Mobile mapping isn't new. Norwegian Public Roads Administration and the counties and municipalities have a lot of mobile mapping solutions. And other private companies also have a lot of mobile mapping solutions. Without knowing the facts, but I would guess that the main roads in Norway is probably driven by private and public mapping companies 10, 15 times a year, or different companies mapping the same road, because it's really important for everyone that's going to produce any type of services. So NPRA, we have mobile mapping solutions, and we collect at least the entire road network for NPRA, so 10,000 kilometers we collect every year with LiDAR and imagery as well on top of other sensors. And this is a gold mine, because we have a lot of data that we can utilize to find a good and to try to figure out what do we have and what is the actual condition of it. So far, we have been taking pictures and we've been looking at them, but we haven't really processed them properly. So what we now need to look at, and this is something that my colleague Christian will talk about later, is how we can use this gold treasure that we have with imageries from all the state-owned roads and most of the county roads. So it's around 50,000 kilometers of road where we collect high quality imageries every single year. And we've done this and we have data all going back to 2014 and it's continuously updated. And this is something that we need to tap into to start to really use it to get a good overview of what do we have and what is the condition of what we have for the static part. And it might sound like a little bit, but this is already done. Yes, it is already done. But what's not done is that we as a public road authority, we don't have the capabilities to consume it and to actually process it properly. So we need to then work on to how we can actually process the data and actually use it for multiple purposes once we get it processed and use it for in many processes that we do on a very manual level today. We have one example that I just want to highlight on the where the mobile mapping and the processing of using machine computer visioning is extremely more effective. Rail guards is something that we have a lot of, and we have been collecting that in the past by driving slowly and manually looking at the rail guards. Now we can use machine visioning, driving in normal speed, and we increase the collection by 1,400%. And then, of course, when you process the data as well, the total gain of an effectiveness is much higher. But also, like the previous presenter talked about, there's a lot of fixed cameras. We don't have that many, but we have quite few. We have public cameras that are for public use, but of course also our traffic management centers have many cameras. In Norway, the traffic management centers have roughly 13,000 cameras that they can use to monitor and look at the roads. And that's usually, it's very good, but at the same time, those cameras can be utilized for many more purposes. So one camera was intended for one thing, but it can probably be used for many, many more. And I was also looking for some pictures for tunnel cameras for this presentation. And I happened to find in our imagery bank a picture of two cameras outside our tunnel. And even though they might not be the exact same cameras, but the point is that one is for detecting the light. So there's a lux camera, and the other one is to monitor a barrier. Maybe we can find a way and make it more effective, but instead of having multiple sensors on one place, we can increase the use of the existing ones for multiple purposes. And that means that we need to build solutions and capabilities to be able to do that within the Norwegian Public Roads Administration. So based on all of the work that we've done over the years, we have created an AI strategy. And that was something that was done last year. And the strategy is based on the insight and the knowledge that we have gained over the years on what we have done and how we worked and what are the possibilities and capabilities. And I'm really pleased that one of our main areas is under physical inspection. There is a lot of other parts within our AI strategy that is important, but for the many of the areas that is important for NPRA, it is the physical inspection, and it's the computer visioning that's really is an area where we need to spend even more time. Even though we have done a lot, we need to set it in more in system and being able to do this at a larger scale. And larger scale is hopefully something that my colleague Christian will show you a little bit more on how we have done this based on this AI strategy and how we then can actually operationalize this strategy. So by that, I say thank you.
Thank you. Any questions in the chat.
There's one from Yana. How often do you do mobile mapping of roadways? Do you use 360-degree camera?
So normally it's once a year, but sometimes it's even more frequent. We tend to drive only in the spring, summer, and autumn. But the rule is once a year, but then some areas is driven more often. We have a mix of different mobile mapping systems. Some have two system camera solutions, and some have 360 camera solutions. And then together with LiDAR systems or without LiDAR systems. So there's the variety of solutions, but then still not that many.
Great. And Torgeir raise your hand if you want to go ahead and unmute yourself. Torgeir? Oh, well, there's a follow-up from Jonna. How are you doing automated physical inspection, LIDAR?
Yeah, so yes, so we also, so as the one of the car that you saw on the image, I also have a LiDAR. So when we do the scanning or when we drive, most drive is done with a LiDAR and with a camera solution. And that's also an area where we're now working on is to combine those two to make for visual, but at the same time that increases the accuracy of our detections from the imageries and so on. So that's also a good way of doing positioning even better, where we have LiDAR and imageries. Where we have only imageries, of course, our positioning isn't as accurate as if you have the LiDAR.
Great.
Yes.
And Torgeir, I just allowed you to unmute yourself. So if you wanted to go ahead and unmute yourself, you should be able to speak. Give you a little time.
All right, it sounds like it's not working, but maybe he can put something in the chat.
Yeah.
Maybe we should move on and then we can circle back. Please put things in the chat if we're not able to communicate. Okay, so we have our next presenter, Christian Shetna. He's also from the Norwegian Public Roads Administration, and he's going to be talking about building a computer vision platform for transportation infrastructure.
Thank you very much, Melissa. Let me try to share my screen here. There we go. So my name is Christian Shetne. I'm a senior engineer at the ITS Technology Department of the Norwegian Public Roads Administration. I'm going to talk a bit about the current tech stack that we have implemented to help facilitate and professionalize the usage of computer vision machine learning models in the MPRA. So first of all, what are the issues that we've faced with implementing computer vision models in the past? So we only managed to implement a rather small amount of different initiatives into full production systems. And even then, there's been some big problems with these solutions. First, it's very hard to go from a good idea to a full-blown solution. It requires a lot of resources and time. And it's hard to get a good overview over what's available in terms of models and what kind of performance you could expect from these models. And once you have a solution in place, how do you ensure that the model's quality remains high and doesn't degrade over time? And there's more problems as well, but these are some main problems. So the first puzzle piece is our new data platform, which is called Saga. Saga is a general data management platform. It's not specific to machine learning, but it's a good framework since like machine learning requires shuffling large amounts of data around and keeping track of where the data comes and where it's going. So Saga handles the collection, storage, analysis, processing, reporting, and sharing of the data. It's covering the value chain from data reception to the end user for both internal and external sources. It's kind of the underlying layer of our solution. Next, we have a very important part of basically any computer vision machine learning model. It's the image annotation. It's a very time-consuming job of labeling thousands of images in order to construct a data set for training, testing, and validating models. Since this is a very time-consuming part of the process and often requires field experts, this needs to be very streamlined. So we are using SuperAnnotate for this. It's quite simple to use, and it offers AI-assisted annotation. And it also supports annotation of LiDAR data, which is, as Gjermund mentioned, a quite underutilized data set. And we have tons of LiDAR data that is it's not being used for its full potential, basically. And then we have orchestration. So orchestration is the automation and coordination of all the steps involved in a machine learning workflow, like data preparation, training, evaluation, deployment. So they kind of run in the right order and at the right time with minimal manual intervention. And we use Flight for our orchestration. It's purpose-built for machine learning and simplifies running the clockwork kind of our pipeline. And then we come to the models themselves. In order to keep track of our models, we use GitLab Model Register. This helps us organize the models we make and makes it simpler to find existing models that may be repurposed for other tasks. Then we also have GitLab experiment tracking. This helps us when testing out our models, maybe tweaking old models as well. We can see how performance metrics and indicators evolve over time while we're testing different iterations of our models. So this is kind of our standardized machine vision workflow. You start by either having your own or picking from an existing set of internal image sets that we already have. So the road images that Gjermund mentioned is among those internal data sets. And then you select the images you want to use for training and validation and evaluation of your model. And then you start the strenuous task of annotating images. And then you either pick a state-of-the-art model or you use your own. Train the model, track the performance metrics to pick the best performing model. And then you can run the model to process your images, and then you're basically done. Here you have the same workflow, basically, just in a kind of a flowchart. You're starting with the image selection and annotation there on the left, and then you're finishing with the delivery of the data set on the right there. And you can also see the model registry and experiment tracking, so you can feed back into the system for future use and reuse. We created a machine vision template for use in our ecosystem. The developers can use this as a starting point when they create new projects. This offers a standardized workflow as a common starting point, while also giving the freedom to adapt it to like project-specific needs that you usually have. So onto the value. So the value for our users, it's way simpler to go from a good idea to having a solution in place without a lot of custom stuff having to be made. You also have more control over the models and the quality of the models. You can do continuous training and improvement of the models you already have. You can reuse components and models for different use cases. And we can finally stop with this one solution, one model thing that we've been doing for the last few years, and start to professionalize kind of the way we're doing handling all the models and the solutions. And it also allows us to use privacy-sensitive images, because we finally set in place a good way to handle these types of images. As for the data scientists themselves, they have experimental freedom to do more in shorter amount of time. They have symmetry between the experimental phase and the operational phase. And what they do is reproducible, it's verifiable, and you have traceable results. And you can do local development, debugging, and testing. And basically, the only requirement is that you need to know Python, basically. So the current status of the project or the solution is we created a new production system for anonymizing road images to be able to freely share and use all the images that we take of the road network every year. Not only does this make it easier to use the images internally for different projects, because you don't have to care so much about the privacy issues, but it also makes it possible for us to give open access to them for the general public. So we've set up a web page. It's kind of similar to Google Street View, which you're probably familiar with, where everyone can access our images and roll back and forth in time and see how the road network has evolved over time. We also started working on models for detecting road signs. We're starting with speed signs now. This allows us to improve the data quality and make systems like intelligent speed advisory work better. And that obviously is a hot topic in Europe, because every vehicle is now has to have ESA alerts on by default. And even if you turn them on, they will turn back on again when you restart the car. So we have to put resources into getting the data quality higher. We also started working on models for feature detection in LiDAR images. So this existing data set we have is greatly underutilized, as I mentioned, and we hope to get a lot of value out of the data that we already collect for other purposes. It's kind of the same thing with the road images as well. We collect them for different purposes, but there's potential to use them for tons of different things. And moving forward next year and even more, we want to look into better supporting commercial models as well. So we're not trying to compete with commercial solutions. We're trying to integrate better and basically keep the commercial solutions on their toes to constantly improve as well. And of course, we're constantly also looking for more new interesting use cases that we can use computer vision machine learning models for. So we're open to good ideas. Yeah, I think that's basically it. Are there any questions?
Yeah, thank you. That's great. We do have a question. Do you have workforce trained in AI to do all the modeling? How big is your AI modeling group? Would commercial solution be cheaper than developing in-house?
So our hope is that we don't have to have a specialized workforce to do everything here. The goal is that we might have some experts that can aid the more generalized teams to do the development of the models themselves, and hopefully the toolbox we give them here is so user-friendly that it doesn't require super in-depth knowledge about building machine learning models. That's the hope, at least. And the AI modeling group is not very big. but we'll see. We try to teach more and more people how to do it. So commercial solution be cheaper and developing. Whether or not a commercial solution will be cheaper than developing in-house is difficult to answer. It depends. We hope that a lot of the more, let's say, simpler use cases could be done quite easily in-house. But obviously, we need to leave room for more advanced commercial solutions as well. But this might also help, I guess, push the commercial solutions into innovating when they know that we can do the more simple stuff in-house. They have to evolve and bring something new to the table, basically.
We have one more question. Can we use different YOLO version or any other algorithm for object detection in the platform?
Yeah, that's the idea, that you can use like existing state-of-the-art open models and then retrain them, basically. Or you can build something from scratch as well. It depends. It's supposed to be flexible in that sense. Yeah.
I saw we had a hand raised. Tamita, are you able to unmute that person?
Yes. I don't see a hand, but feel free to go ahead and raise your hand again if you had a question.
And we'll also have time at the end, so we can come back to questions then. Okay. Thank you, Christian.
Thank you.
So our next presenter is from the Washington Department of Transportation. Her name is Garima Tawari, and she will speak about enterprise AI governance and implementation at WashDOT.
Thank you, Melissa. Can someone confirm if you can see my screen?
Yes.
Yep.
Wonderful, thank you. All right, good morning, everyone. My name is Garima Tiwari, and I serve as the Assistant Director for Enterprise AI and Data Services at WashDOT. I would like to start with thanking my co-panelists for sharing incredible insights around AI, machine learning, computer vision, and edge computing, all fascinating stuff. Today, I am excited to share WashDOT's AI governance strategy and vision with you all. Before we dive in, a quick disclosure: these slides were prepared by humans, verified by humans, though we did lean a bit on AI for assistance. Let's look at where WashDOT stands on AI front today. To ground our conversation today, we look at our approach through three incredible simple questions: the why, the what, and the where. Why are we doing this? So, transportation fundamentally runs on data. If we want reliable AI, we have to start with strong, trustworthy data foundations. That is how we improve safety, efficiency, and mobility for the public. And what are we building? We are actively avoiding a Wild West approach. Instead, we are establishing a governed enterprise strategy with responsible use guardrails and repeatable path to push secure tools forward. And we are moving rapidly from isolated early experiments to a more mature agency-wide AI ecosystem. Our focus over the next 12 to 18 months is scaling literacy and high value use case across all divisions of WashDOT. With that, let's look back briefly at how we got here. So in 2025, our technology service division made a structural shift by formalizing the enterprise AI and data services team. This effectively moved AI out of the technical sidebar and made it a core enterprise strategy. Then in April of 2025, we established our leadership foundation by creating a dedicated assistant director role. And we also are working on hiring a data architect to spearhead enterprise-wide governance. By June of 2025, we broke down operational silos by launching an agency-wide AI working group serving as our community of practice to kind of build shared literacy. And in December of 2025, we achieved a major milestone by publishing Watchdot's first formal guidance on GenAI assistants. This was heavily reviewed by our privacy, security, legal, and communications, and officially approved by our exec committee. The result is highly mature, well-governed framework that pairs rapid innovation with absolute accountability. Governance is the cornerstone of our program. As the Assistant Director for Enterprise AI and Data Services, I serve as the single point of accountability for AI strategy and governance within TSD. For exec oversight and approvals, our team reports directly to the end user committee. Operationally, our governance model splits into three distinct layers. First is the discovery and engagement. This layer primarily monitors cultural readiness, manages our use case pipeline and AI inventory, and connects legal, HR, and business units to share institutional knowledge. Second, we have governance itself. This basically covers the policy, risk, and strategic alignment. It defines what is acceptable use case mean, conducts reviews, ensure strict data hygiene, and keeps us aligned with our 1 to 3 year roadmap. And thirdly, we have operationalization. This is basically our technical intake engine, which manages strictly like risk and return of investment analysis and translate the policy into hard technical guardrails such as SSO or robust encryption, etc. Our roadmap and investment are anchored on four fundamental guiding pillars. First pillar is data as the foundation. Trusted, well-governed data is a strict prerequisite for reliable AI. Pillar 2 is responsible and secured. So we embed privacy, security, ethics, and explicit state policy into every single use case we are touching. Pillar 3 is enterprise, not silos. We maintain one coordinated program with consistent standard that scale across all division, preventing fragmented tools. And fourth pillar is value-driven adoption. We focus our energy on high-impact use cases with clear return of investment as they progress from pilot to full production. All of this is obviously not figured out, but we are working towards the golden rule of ensuring that we abide by our four pillars that we have established. Ultimately, our commitment is ethical and responsible use. Our goal is greater business and customer value, and our approach is firmly human in the loop. We have two-pronged strategy. The first step is to boost everyday employee productivity so that we can free their time to kind of, invest that time that they save in more useful technology-driven stuff. And then augment human capability by automating repetitive tasks and practical application of AI. Moving on to this next slide, because data is our foundation, we are actively revamping our data governance framework as well. Starting explicitly with one of our portfolio, multimodal development and division. The goal is to build a highly successful model here and replicate it across every other portfolio in the agency. Our strategic goals are clear. We want to know exactly where data exists, what it is, improve quality by assigning clear business owners, enable data-driven decision at all levels, and standardize both our data analysis toolset and production storage. We are executing this through a disciplined phased approach. We are in phase 1 currently, which is called discovery. We have spent time surveying and interviewing TSG champions and business reps to assess the gaps and challenges on our data governance. We'll be working on discovery report and a formal multimodal development and delivery data governance charter as well. Next, we kick off phase 2 basically, which is exploring automation tools via vendor demos, drafting policies, and establishing the final framework. And the plan is in the first half of 2027, we'll implement phase 3, which will basically deliver our long-term roadmap, and we'll be able to run a dedicated pilot project to prove the framework so that we can take it forward and repeat it with other verticals at Watchdot as well. So to give our employees the confidence to innovate safely while reducing compliance risk and shadow IT, we have laid out clear agency approved do's and don'ts for GenAI. On the do side, we absolutely encourage using GenAI for research and brainstorming. However, you must always verify all generated content, check for inherent bias, be fully transparent about your AI use, apply human oversight, and strictly follow existing agency policies. On the don't side, I think no points for guessing, because never under any circumstances input any sensitive or personal data into any public assistance. Do not share the privileged information, do not allow AI auto-generated public policy, and never let it replace your professional judgment. Lastly, do not hide the source of your work and do not ignore our state records retention laws. That is super critical. Let's talk about our Microsoft 365 Copilot pilot that we did with 1,000 licenses. We designed a thorough evaluation process that included Microsoft-led hands-on training and self-paced videos, 3 dedicated office hour sessions to capture real-world employees' use case, and a highly structured feedback loop to evaluate value and gaps before making wider rollout decisions. Our trial licenses formally ended in May of 2026, and the user feedback data we captured is fascinating. As you can see from the chart, a clear majority, 64% of the participants affirmatively requested that we buy the license for them if possible. 18% noted that they would prefer a different GenAI assistant instead, while 17% stated that they did not find the tool useful for their specific workflows. This data is now sitting with the leadership for an exec decision on our next steps. Of course, our AI exploration extends far beyond just, GenAI Assistant. Work is actively underway across multiple divisions, partnerships, and procurement channels. At the division level, we are piloting tools like ChatGPT, Notebook LM, and other custom Washdot-grounded RAG implementations and tailored AI chatbots as well. At a national level, we are collaborating with Federal Highway Administration and other state DOTs through the State DOT Council for strategic AI adoption, ensuring WashDOT has a voice in the National Transportation Pooled Fund studies. From security perspective, we are partnering very closely with Watchdog TSD to conduct comprehensive security design reviews of the GenAI assistants before they are adopted widely by our staff. And regarding procurement, we are currently working with Microsoft and OpenAI on a secure paid enterprise AI licenses, along with the ongoing discussion for wider Copilot chat rollout as well. Technology is only as good as the culture using it, which is why building AI literacy across our workforce is another top priority for us. Washington has entered a partnership with Innovate US to make responsible AI training available to all agency employees. This curriculum is tightly linked with Washington's state Data 04 AI policy and will be delivered directly through our internal learning management system. This initiative is currently in formal review with Watch.HR. As we look at our 12 to 18 months roadmap, our target is clear: mature from governed foundation towards scaled, high value AI agency wide. In the near term, our focus is decide and deploy. We expect an exec decision on the partial Copilot rollout for interested employees, finalization of our ChatGPT enterprise procurement, and full launch of our AI literacy courses in LMS. In the midterm, we will focus on scaling use cases. This means officially standing up our formal intake engine, expanding our grounded RAG tools and chatbots, and embedding AI risk assessment and security reviews as an uncompromised standard. On the horizon, we will continuously mature and measure. Will track strict our return of investment and adoption metrics, deepen our Federal Highway Administration and state DOT collaborations, and advance our broader ecosystem. Everything we'll do will remain secure, governed, and aligned to Watchdog's core goals. So to leave you with a final summary of Watchdog's approach, we put governance first, anchoring our work with single accountable leader and structured committee oversight. We are trying to provide clear guardrails through agency approved guidance so our staff can innovate with confidence. We are prioritizing people and literacy through our community of practice and upcoming statewide training. And we have clear path ahead via a concrete 12 to 18 months roadmap to build a mature, measurable ecosystem. Thank you all so much for your time today, and I'm very happy to open up the floor for any questions that you might have. Thank you.
Thank you. That was great. All right,
Thank
we're
you.
just looking into the chat to see. We have some accolades from your coworkers. Do we have any specific questions for Garima before we open it up to all the panelists? Okay, well then we're going to spotlight all of the panelists and we're going to have question and answers. So going to the top of our chat list, I think there might have been some for Yin Hai that came in after your presentation. John Milton from WashDOT asks, we have significant challenges in rural to suburban locations, often because of data gaps. Our ability to make real-time decisions is affected by this challenge. How do you see Edge AI helping with this?
Thank you, John. This is a great question. Actually, I've been also thinking about these things through my work with like WashDOT and also the tribes in our area. So I do consider, given the rural areas lack of power, right? So I think some solar power-driven solution will be a good fit. And this agentic edge AI, let's say if there is a particular roadway curve with a lot of departure crashes, if you could have this like a agentic edge AI monitor this particular segment of the road and finding, for example, if the road surface is becoming very challenging, like covered by snow or black ice, and then you could generate a warning, right? If we could also install the variable message sign, we could deliver the message to tell the variable message sign to show like black ice on the surface, control your speed under 10 miles per hour, for example, right? So these things will be very helpful, and we do not need to be really sending the detection result to the nearby traffic control center and get the traffic engineer's decision on this, because the technology now is getting pretty good result. And this kind of technology, you do not need the power supply, and you do not need like a communication system support. Let's say if there's a cell phone data, you know what's going on, right? If you want to see how the technology has been performing, you could look at the system log to see when it triggered a kind of a warning message, and the evidence image, right? You can look at that to see if the system is performing as expected. If yes, you could keep it going. If not, you could make some modifications, try to make sure it will be detecting and making the right decision accurately, right? So I think this technology, in my opinion, is better than anything else I could think about, right? So in the rural area, your challenge may not be simply detecting the road surface condition or the visibility. Sometimes you want to see, is there a nearby wildfire or other challenges, right? So by deploying other different detection algorithms, you could make it work as different kind of sensors. So I just feel this is so promising. That's why, I'm promoting this technology through, the conferences and also some of our webinar opportunities. So I will stop here. Otherwise, I can keep going. So, John, I hope I answered your question.
Okay, and we do have Torgir's question here. And I'm not quite sure who this is targeted to, but I'm sure the panelists can figure this out. My question was, how do we know that a collected picture is of value and to be stored in the image library? And how do we label the pictures?
I guess that might be for me, maybe for a selection of images for training a model. In which case, I think it's a very good question. The important thing is that you have like a representative amount of images. You have a separation of like time of day and time of year, preferably. So it's a good representation of what the images that will be used as input will be. Now, if you're using road images, they're usually taken at a similar time of year. But that also probably means that your input images will be the same. But then you'll have stuff where we've seen problems before, where you will have a low representation of, for instance, tunnels. We have a lot of tunnels in Norway, and you need to have enough tunnels basically in your training data in order to expect to get good results for doing image recognition, for instance, in tunnels as well. And the images we capture have obviously a lot of metadata associated with them. For instance, they have their location, so in which case you can actually pick out training data specifically from tunnels or areas where we have tunnels. So I think the best thing is to try to get a good coverage, figure out what kind of conditions you will expect in your input data, and then use the available metadata in the images from the images we already have and try to select a broad selection. But it's very important that you have good coverage, basically. And it's also kind of, you have to have coverage from the north of Norway down to the south because it looks very different. Yeah, it's a good question, and it's not trivial for sure.
Maybe I can also add something to what Christian just mentioned. I think diversity of the image data is very important, particularly if you want to move an external model to apply to your internal business, right? So there are normally the transfer learning engaged. The better the quality the data you have, the better the result will be. But certainly there needs to be a balance, right? How many images do you want to store, right? Because the image takes the space. I think selecting the representative images will be great. Certainly this will also require some expertise on, what kind of model you'll be training, right? And how, you could properly label these images. But in general, I think now the development on the AI side is very fast. So with a lot of good quality images, sometimes the computer science community want to generate new data, like using the diffusion model. You feed the model with the kind of images, and then you tell them what you want, and they could generate something, right? So I think the video language model, all kinds of models seem to be understanding the video images better and better, right? So I think getting some images stored, as far as you could have the space and affordable, for those images, I would say try to keep the data rather than dump them too early.
Okay. We have another question. Do you have an estimate budget or the ideal sufficient AI staff system operation cost over the short 3 to 5 years and long term 10 years or more term, given the additional increased infrastructure cost, camera, sensors, power source in the rural areas or certain identified needed areas?
I guess this question is also to the agency folks, right? Maybe Garima or, George.
I can maybe answer it in a way that because one of the purposes I've mentioned by what we have shown and what we do in Norway is that we do already have a lot of infrastructure in place. So we will see how we can utilize the existing infrastructure instead of adding more infrastructure because it is costly, and was also mentioned about that we actually don't have the capabilities and the need for a power source and so on in the rural area. So to utilize the current infrastructure for more purposes. And then something that's also maybe to the other question, also what Ian Hai was talking about, is that we also were looking at using the actual cars as a sensor. So instead of just putting it on the road next to the road, we utilize more of the actual cars that are actually driving. Either, of course, by putting a simple mobile phone, which also have capabilities of edge processing, but then also using the built-in systems in the OEMs. This is something that they already monetize on, reselling detection that they do. So, for example, we have in the past been purchasing data from OEMs and then using that to detect where we find missing speed limit signs for our national road database, as an example. Or we use the same type of data for detecting weather, accidents, and conditions, road pavement, and so on, also from the OEMs and the systems that are already in the cars. So I think it's a good way of looking at differentiating so that you can have high quality on the mobile mapping solution systems that we looked at, and then the differentiation down to the the lower quality but the high frequency when it uses the fleet of cars that drive around. And it's the same thing with other solutions as well, that we then build and see what can fit to the different purposes, and not to lock into one system, but then also look at what kind of capabilities do we need to have. Sometimes we need to buy solutions, sometimes we can build and find a good mix in what we do. And this is changing very rapidly. So from our colleagues, and I think what Chris also mentioned, is that at the moment we can actually build solutions and systems that means that more of our colleagues can actually utilize and use the systems and be able to take part in training and so on with the tools that we make available for them.
Maybe I can also share some of my thoughts on this. My lab has this spin-off company, right? So this company recently, because of the visa issues, right, some person left, and they recently hired one person. This person actually knows how to use a bunch of AI tools, and he was able to handle 2 people's work and do better with the AI tools. So I would say if there are some mature technology become available, right? So you probably want to use those new tools and try to see how you could improve the work efficiency, and in a lot of cases also the accuracy of the work. And then you could have staff to be exploring many new ideas. So you see maybe recently like the beginner programmers, they are kind of hard to find jobs. And this is actually due to a lot of AI tools can do so much better and faster, for the fundamental repetitive work, right? So I think if you see agencies have this kind of work could be better done by AI, you could try out. Maybe they end up to be doing a better job, and that will be addressing our workforce challenges, right? Now we don't have enough people, especially the experienced persons, to do a lot of work. But also through my discussions, with the local technology leaders, and we have somehow get the kind of consensus, what AI is good at is normally the kind of repetitive work. But if you want to make decisions, you don't want to trust AI to make decisions yet for important things relevant to people's life, right? So in this case, you may actually make AI to be doing a bunch of work that is, saving human hours, labors. And then you could see maybe several alternatives AI generated, right? And you can find which is the best one to use. So for the important decisions like scale, like network level decisions, I think experienced engineers' role is super, super important. But making a good use of the AI tools to handle the fundamental issues, I think will be a good deal, right? So if you allocate some budget to address these things, I would say that may be a good use of the funding.
I'll just add to that, if I can, just having that risk assessment, some sort of matrix to ensure that where the way Professor Wang was saying, like, where we have to apply AI, we need to also understand and ensure that the risk is minimal, so that we are not impacting the real public out there. And if we can master that recipe, I think that will really help us utilize AI, apply that practical AI for applications and systems, and ensure that we get that, repetitive work done faster and more efficiently. So just wanted to say, it's very important to have that sort of governance and the risk evaluation assessment criterias identified well in advance. Uh, but yeah, I absolutely agree with all that has been said already.
Wonderful. Thank you, panelists. We have another question in the chat, maybe targeted towards Norway. Do you have any restrictions on using cameras on roadways? At Washington State Public is worried about privacy. It takes a long time even to test AI-based cameras on the roadways. It took more than 4 months just to get a permission to test an AI camera from a vendor. What are your experiences?
I guess the short answer is yes, there are restrictions.
Yeah.
But there's a difference between the fixed cameras, like the webcams we have, and the vehicles that take photos. Even, I guess the rules aren't different, but the way you have to handle it is different. So in the case of the fixed cameras, they are already now they've turned down the resolution of the images a lot for the public access. Like a road operator could go into the specific camera at a specific time and view the high resolution one, but the continually streaming images are lower resolution, so you can't really see faces and license plates and stuff. But we're also now looking into doing the same thing that we're doing to the road images that we take from a vehicle, is to anonymize it, because we are more interested in looking at the road infrastructure itself or the weather than we are at looking at actual vehicles. And people in the images themselves are really unimportant. So we might as well remove them as best we can. And the same approach goes for the images taken from vehicles. They are mostly taken for looking at the surface of the road or stuff the roadside. So we might as well just remove the elements from the image that are both privacy issues and also kind of like noise in the images in the first place.
And I think it's also, of course, we have a lot of areas within where we actually have a mandate to use the imagery, so like the traffic management centers. And that same camera, of course, can't be used for other purposes because it has a high quality. But be able to then take one camera and actually feed it into multiple different use cases and do different blurrings and so on means that you can, as long as we have the right mandate, we can just stream it to that according to that mandate. And it means that it's easier to do that. And also that we can ensure that we also look at, even though we maybe been hiding behind the challenges because it's easier to just then don't do it. So if we then challenge ourselves and also say, okay, how can we mitigate that and actually do it in a way that we can show that this is for a good purpose, but at the same time take care of all the GDPR regulations that we need to. So I think it's a definitely improvement for how it's been in the past. And then also we can use more solutions on that is also helping us to avoid these kind of things. And I think it was mentioned LiDAR here earlier. So where we can actually use LiDAR instead of imageries for example, detection of pedestrians and so on. So there's a lot of ways where we can make it a little bit easier for ourselves.
All right, thank you, everybody. Looks like we have time for one more question. I don't know if we have any more in the chat. I don't see any, but please.
Melissa, there's one in Q&A.
Okay. But not in the chat?
not in the chat. So the audience normally asks through Q&A. Yeah, let me read
Okay.
the question.
I
Do you
see it.
find
You
it?
go ahead.
As you mentioned, a more diverse training data set is needed for object detection. However, if the goal is to extract the exact geospatial location of an object or vehicle, is data augmentation still necessary to increase the diversity of the training data set? So that's the question from Samin Nahar Mila.
If it was for me, maybe. So we already, for some vehicles, take LiDAR data as well. So we are going to look into augmenting the location data already available in the image EXIF data that we have, which is, so when the photos are taken, they're already geospatially referenced. But we could augment that with the LiDAR data we already have to get even higher accuracy for objects that you see in the image, not just the position of the vehicle that took the image. But you could also do stuff with the images themselves to extract the location for objects seen there. If you have multiple images of the same object, for instance, you can do some fancy maths and figure out where the object is in the real world. So that's being utilized as well. It kind of depends on how accurate you need the positioning to be. In some cases, maybe it's a precise location of the object isn't that necessary. So maybe the location of the camera is good enough. In other cases, you might want a really accurate position, and then in that case, maybe the data augmentation with, for instance, the LiDAR data is necessary as well.
So I will also add to this question. I think depending on the needs, right? If the need is only to locate the detected object, right, a vehicle or other object, this is not just simply machine learning problem. It is more of a matching problem, just like autonomous vehicles, right, driving on the road, and the car wants to know where it is right now, right? So normally you need to be comparing what the car sees to the 3D map, right? So this is a kind of matching issue. So adding extra data set may not be needed. As far as you have a good set of data and your car or like the information you can provide to users, the matching is sufficient, right? So I think it's a different kind of issue. Maybe spatial intelligence related technologies will also be helpful, to solve this problem.
Yeah.
Any other questions to us? It looks like we control the time pretty well. If there's no other question, Melissa, I think we're exactly at the scheduled time.
Yes, thank you everybody for coming to our webinar today. We really appreciate your questions and engagement. We will be sending out PowerPoints. If the presenters can share them with us, we'll share them with the audience. So thank you everybody for attending. It's great to see you.
Thank you.
Thank you.
Have a nice day, everyone.